So in the last lecture, what was done, we discussed the pressure, right? And we also realized that pressure is equal to rho gh. I think we have derived the pressure formula, right? So the pressure due to liquid column we have derived, yes or no?
Yes.
So now if we have a vessel of shape like this, and if it is filled with water, then the pressure depends on what? The pressure depends on the depth of the point from the free surface of liquid. So if I take a point here, let's call it A, then we should not take this length. No, we should take the free surface length or depth. You can say. So wherever the point may be, the pressure depends on how much is the depth of the point from the given free surface, the open surface, which can be anywhere. So this height will matter, not this height. So if this is H dash, if this is H, then definitely H will decide the net pressure at A, not the H dash. Okay. So this is what you have to remember, that pressure H, it is calculated from free surface of liquid, not from the liquid level above the point. So imagine if I name it H1 and H2, and let's say the diameter of the cross section. So let's say this diameter is A. So it's a circular shape object. So what we are looking at is the cross sectional view. Okay. So the pressure at A will be how much? What is the pressure here? So even if I take the point B here, or if I take a point C here, because A, B, C belongs to the same level, so they must have the, yeah. So this will be rho G,
H1 plus
and
H2
always
plus
add
rho ATM.
plus rho T. So it will experience the liquid pressure plus the atmospheric pressure, and all we have to add. So we never look for the liquid level above the A. We look for the liquid level till the free surface, which you can reach through. So even if we have a closed container filled with liquid, so let's say we make a dent here. so that air can enter a small hole, not a big hole. So once you open this part, and if I choose a point here, then the pressure at A will be exactly same. If I say this is H, then this will be PATM plus rho GH, because if I look at the free surface which is here, and if you look at the A point which is here, the vertical separation between them is H. So what matter is the vertical separation between the free surface and the point taken, and it has nothing to do with the location, just a vertical separation. So you may create a tube like this with some random shape and opening, and what is interesting to know that the pressure at a point A will depend on this surface free, which is free surface, and the level of A point, and then we take the vertical separation. So it has nothing to do with the what goes in between. Understood?
Yes, sir. So, but what? So, like, it will also have the particle present in between. Also, will exert like if it will be like a rectangular box, and the particles present in that area volume will also exert pressure.
No, see, when we say pressure, then we talk about the macroscopic phenomena. It means what is happening at the microscopic level, we are not concerned about. So rho GH will take care of everything. You need not to worry about what kind of collision is taking place there and how it is being exerted. So that is not your concern. Understood?
Yes, sir.
So now what we can also realize that okay, this was in context of this problem.
So,
Yes.
so in the first diagram, the A part, it's the pressure is equal to the pressure on the B point as well. So is the glass tube above the A point responsible for the equal pressure?
Exactly. That is the question we are going to discuss only. So how it manages? So the idea is simple, that the pressure at this level is everywhere same. So at this level, we can say pressure is how much? Rho GH1. Correct. So the wall at this level will exert extra pressure of rho GH1, and then the liquid column will add up to rho GH2, and the sum is rho GH1 plus rho GH2. So you can say that the mismatch is due to the wall. So we can in fact calculate what is the pressure exerted by the wall, and the answer is simple. So the pressure exerted by the, let's name it something, call it what you can say, surface S1 and surface, okay, this is one surface basically. So let's call it surface S. So this is a surface actually, like a disc shaped surface. So the surface will exert by the surface S. And to know the pressure, the force by the surface or the pressure by the surface, look at the depth of the surface from the free surface of liquid. So this is free surface of liquid, and here we have the surface. So this depth will matter. So we can say rho GH1. So the part which is under the surface will experience two pressure, one their own liquid column, which is H2, and the pressure which the surface is exerting on the same liquid. So even though it is not facing the free surface, the pressure is arriving there. Understood? So the pressure of this column is part of this surface everywhere. And because the liquid is applying pressure on the wall, so in return from Newton's third law, the wall is exerting pressure on the liquid in the downward direction. And that is how it maintains the pressure throughout the volume. So at a one level, whether you pick A or pick B or pick C, the pressure remains same at every point. Is this clear? Understood?
Yes, sir.
Yes, sir.
So they may ask you that find the the net force applied by the surface S. So F net by surface S will be how much?
Rho g H1 into area.
Into pi B square minus A square by 4, because that's diameter. Correct? There's a circular shape actually. This is like this. I hope you can understand. I'm bringing this part. So this is the pressure analysis part, and we should be, comfortable with this kind of calculation. So this leads to the concept of something called hydrostatic paradox. So okay. So you can see here, we have three vessels with the same base area. So base area is same in each case, but different size. So they can accommodate a different amount of water, but the height is same again for every vessel. So what this paradox says that it says that if you connect every vessel, So this is called the communicating vessel. Communicating word is, I think, clear to you guys. You know what is the communicating.
Yes.
So if you start pouring liquid in, let's say, first vessel, the water will rise up to the tube, and with the moment you reach the tube level, the water will go to the second, and then will go to the third. And when all three will fill up to the same level of the tube, then the water will start rising. But again, it will keep on rising exactly same for all three. So water will rise by same level. The reason is simple. The flow occurs due to the difference of pressure. So water will flow till the pressure becomes equal. Now for the pressure to be equal, the only thing required is pressure, and pressure depends on the level. Like what is the depth of the point from the free surface, and you can see the every free surface is same. Now because the base area is same, so it really doesn't matter how much is the amount of liquid, and therefore the pressure at this point or this point or this point, even if you take a below the wall, pressure at every point is going to be equal. So pressure at A equals to pressure at B. So pressure has nothing to do with the amount of liquid. It has only to do with the depth of the point from the free surface, nothing less, nothing more, nothing less. It is clear?
Yes, sir.
Now, what is paradox? So paradox is this. If I put a weighing machine below it, so the reading of each will be different or same?
Different.
So different.
Yeah. So the reading depends on what?
Amount of
So the reading depends on the weight of the vessel, the weight of the liquid you can say. Let's say vessel is having negligible mass. So imagine the vessel doesn't amounts to any mass. So the weight of the liquid will rise, and so the net weight, and so the reading of the weighing machine, because weighing machine measures the normal reaction, correct?
yes,
Yes.
sir.
But the confusion may arise here that the pressure is same, so the force should be pressure into area.
Yes, sir.
Is normal is equals to pressure into area? Yes or no? And the base area is same. So can you say the
No,
normal
sir.
No, sir.
No. No, sir, because the walls will also.
correct, because the side walls also will have the extra normal. Okay.
Yes.
So the normal will balance the net downward force acting on the everything, which is the weight of the object. So pressure into area will not give us the normal reaction. That's why you may go wrong if you think in that way. So having equal pressure will not guarantee that it will have equal normal as well. Okay. Okay. So okay, we can go next. So have we done the barometer?
Yes, sir. We have done.
Okay. So after barometer, what we have new device called manometer. So manometer is something which you have already studied in the gaseous state in chemistry, because it is widely used for like in various numerical which you solve. So manometer is a device we say that it is used to measure the gauge pressure or gauge pressure. How we say? Yeah, I say gauge pressure. So it is a device which is used to measure the so what is gauge pressure? So we can say gauge pressure is pressure above the atmospheric pressure of so P gauge is P minus P ATM. Okay. So P gauge is P minus P ATM. So once you know the net pressure P, and if you subtract the atmospheric pressure, what you get is the gauge pressure. And in most of the scenario, the gauge pressure is important because we know that the working of various devices depends on the change in pressure above the atmosphere pressure because everything is already at atmospheric pressure. So when you make a change above this, you can see the difference. So how a manometer is designed? So let's design a manometer. So generally we have a gas chamber, and you may attach some heater to heat the gas. So because it's a closed chamber, so as you will heat the gas, the pressure will increase, right?
Yes, sir.
So now what we do is we make a small hole. We'll make it slightly large to demonstrate. And through this hole, we attach a U tube. Okay. So we have a U tube which is connected to the this gas chamber, and in this tube, what we do is we fill the mercury. Okay. So you can see there is the mercury which is filled in the tube, and as a result of high pressure, the gas will try to push the liquid below, and this tube is very small dimension, so we can ignore the, we can, I mean, of course gas will expand, but essentially the volume is I mean, same as the chamber, because this volume, the tube volume, is almost negligible. So you can think this is like a thermometer, mercury rising, so that's very thin line. So I can say the gas will not affect, the volume of this chamber will not get affected. That is the idea. So because of the high pressure, so when the gas is anyway at atmospheric pressure, but when you heat the gas, the pressure will become more than atmospheric. So this is P gas, and the liquid is pushed like this. So pressure at a same level must be equal value. That's the basic idea. So at this level, we can see the pressure is due to gas itself. But if you go on the right side at the same level, you can see the pressure is how much. So if I say the difference of height as h,
P-ATM plus rho GH.
correct, and atmosphere is anywhere here because that is what we don't show. But this pressure is P-ATM, which is anywhere actually. So pressure on the right side we can see calculate is P-ATM plus rho g h. So the h is the indication of the gauge value, how much extra actually we have, because we can also equate. You can say P gas is equals to P-ATM plus rho gh. So we can say P gas minus P-ATM equals to rho gh, and therefore we can say P gauge equals to. So by looking at this device and the difference of the mercury column level in the two limbs, we call it limb one, limb left, left limb right. So this is called left limb. So by looking at these two left and right limb and the difference of the liquid level, we can find the gauge pressure directly. So that is why it is used in this particular fashion. Okay. So the next is, so now we'll study the equilibrium of liquids. That is not one liquid but multiple liquids. So we have three types of problem that we generally encounter. So we have U-tube problem, we have V-tube problem, and O-tube problem. So there are three types of problem that we have to encounter. So let's begin with the O-tube, U-tube first. So you can see we have a U tube, and in this U tube we have multiple liquids which are at equilibrium. So let's take the vertical height value. So the first height you can call it H1, the second you can call it H2, the third we take vertical height. Remember only how much vertically it is capturing the space, that is what matters, not the actual shape. So now let's name it. And let's say their densities are different, rho 1, rho 2. These are immiscible liquids, which means they cannot mix. All right. So the first thing you can see that this tube is a open tube, which means it is open to atmosphere, which may not be the case all the all questions. So this is what you have to take care of. This is open tube, and therefore, if any tube is open tube, then near the open tube it will have the atmospheric pressure. Because if you are exposed to atmosphere, then it will have atmospheric pressure. If you are exposed to some other environment, then it will have that pressure of that environment. Okay, so you need to just remember that the pressure near the open surface will be same as the surrounding. So just check which surrounding you are into. If it is atmospheric, then atmospheric pressure. It could be other depending on the surrounding actually. But if you can see clearly that the ends of the tube is open to the same surrounding, then the pressure must be same as the surrounding. So pressure, if I say pressure here is P, this is also P. And this P may be PATM, this P may be something else also. But as of now, I'm assuming just P. So the best way to solve question like this is dive in, dive out method. So this is just, I have named this method as something funny. So what you need to do is you just dip inside the tube from one of the end. You can choose left or right, doesn't matter. And while you are descending, keep on adding the pressure till you reach the bottom. And while you ascend, subtract the pressure till you come back to the open tube, the other end of the tube. And then you can write something. So let's start writing this. So I'm entering from the left. So that's why I've shown the left arrow to dive in. And I will dive out from the right tube. And then I'm going to write the pressure. So now liquid position doesn't matter. What you need to remember that it doesn't matter where the liquid is or liquids are. Just look at the vertical height and what they can contribute because of their own presence. That is what matters. So to begin with, let's come down. So I can start with pressure P, correct? So I enter from the surrounding where the pressure is P, and then I descend through the height H1 of the liquid rho 1. So you can say the pressure will grow by rho 1 GH1. Then what next? You can tell me the answer now. Plus, what we can write?
Rho 2 GH2.
And then next,
So rho 3 GH3.
then next.
For use for
Then if you go, it
So
may be
rho
minus.
minus upwards and minus.
But rho will remain rho 3 only because it's the same liquid.
Yeah.
Yes.
And then going further will be rho 4 GH5.
Minus 2 for GH.
And now you're back to the atmosphere. So can we say this must be equals to P? Because where you are eventually is same as the pressure P, so this P will cancel out. So no. So why we are writing this particular way? There is a reason. So let's say I change the environment between them. So I make sure that the two ends are not in the same environment. So you may be starting with P1 and may end up with P2 because the two ends are exposed to the two different atmospheres. So this way of writing will always be helpful because I mean of course we'll get the right equation. So that is why this is how I write. But as of now we can keep it simple. And G will also cancel out. So you can simply write rho 1 H1 plus rho 2 H2 plus rho 3 H3 equals to rho 3 H4 plus rho 4 H5. Correct. And you can also take the rho 3 H4 on the left side and you can see it's H3 minus H4, or you can take H3 on the right side. So what eventually matters is the difference. So you could have totally avoided writing this part because the left and the right are exactly same with same density, same height. So this will cancel out each other effect. So you could have only written from here and then right here. That will give the same answer. Understood? So if you write the pressure from here to here, bottom, then go right and then go up. Because this part will cancel out to each other effect because they are exactly same. Correct? Understood?
Yes, sir.
So in that case, you have to find this height, which is H4 minus H3. And then you should have written rho 1 GH1 plus rho 2 GH2 minus rho 3 GH4 minus H3 minus rho 4 GH5 equals to, I can just make it 0 because, okay, the beginning and the ends are same. So this will lead to the same answer. Or you can say, I can add P here, I can equal P. That's the same way of writing. So if you can see that the bottom is having same liquid with the same height, you can just ignore that part and solve for the rest part. And the way I explain here. So it is up to you to choose the way of writing, but all ways are easy to understand. The other way of thinking is this also. You can just to make the diagram clean. Yeah. You can also think this way that you come to the bottom from the two ends and equate the pressure, because either you come from this side or this side, the pressure must be same, right? So this is also a way of thinking that we equate the pressure at the bottom from the two sides. That's it. Is this clear?
Yes.
Yes, sir.
Okay. So now in case of V tube, which is just a shape wise different, theory wise, everything is same. So we have a tube like this. So you can see this tube. So you can take any number of liquids, but I'm just taking a few numbers just to for sake of writing. Okay, so now we have and what is given to us is the slant length. We name it L1, L2, L3, and the density rho1. So tell me the relation between all these quantities. So I think you guys can solve.
So we have to just find that equation.
Tell me.
So that equation, no?
Yeah.
Sine alpha into whole bracket rho 1 L1 plus rho 2 L2 plus rho 3 L3 bracket close equals rho 3 L4 plus rho 4 L5 bracket close sine beta.
Yeah. That's it. Very good. So the last question is called O2 problem. And this is very famous. So this question was asked by JE Advanced and JE Men's both over the years. So in this case, we will not fill with too many liquids. Rather, we will have just a few liquids. And now, uh, so now this is the O tube. You can pour the liquid from the top. So initially, it was filled with just two liquids. exactly filling the half of the tube. So it was filled by just two liquids on the left and the right. So now in the very beginning, this is there's a stopper here which will stop the liquid to go from left to right. And you can see we have exactly filled the one quarter, and this is called the interface of the two liquids. And imagine that rho 2 is more than rho 1. Just imagine. So in a normal situation, when there is no stopper, the pressure at the bottom due to the right liquid will be bigger than the pressure due to the left liquid, correct? Yes or no?
Yes, sir.
So it means the liquid will not remain this particular way, rather rho 2 will slide down and the green, sorry, the rho 1 will, yeah, rho 2 will slide down and the rho 1 will, the green one will go up. Okay. So once you remove the stopper, you will have a situation something like this. Let me explain, although I'm not supposed to, let me explain. So it will take a new shape, not new shape, like a new orientation. And this part of liquid will be somewhere here. Let me make it again. So you can see clearly this part will be present here. And this green part will come here because the volume cannot change, right? So only the position will change. And this is going to be the new interface. Okay. So we can see that the new interface will make some angle with vertical. Let's call it theta. So question is find theta or find tan theta. So again, you can do the same fashion. Write the pressure at the bottom by after shifting the liquid, and then so first you shift the liquid and then draw the diagram and then write the pressure at the bottom, or dive in, dive out, do whatever you want and tell me the answer. Okay, do this.
So is tan theta 1 by 3?
No, we have rho root 2, no? So answer must be in terms of rho root 2. How it is 1 by 3?
Oh, sorry, I thought that was a 2 row and a row.
Oh, okay, okay. So in that way, I think that your answer is correct. Very good. Then it's a really good answer. The correct answer. So anyway, you got the answer, which is correct. You could have expressed in terms of rho 2, rho 1. That would have been better. That was the J part. And J asked that way. So anybody else who got this answer? Like,
Last step.
so whenever you see a tube,
Rho 1 minus rho 2 upon rho 1 plus rho 2.
no, because 2 is more than 1, so it should be 2 minus 1. So rho 2 minus rho 1 upon rho 2 plus rho 1.
Sorry, sir. I wrote my mistake. Rho 2 minus rho 1. It will be in numeric.
The answer will be tan theta equals to the difference of density upon the sum. So they asked something very interesting. So first they asked tan theta, then in the next time when they asked the same question, they asked what is the ratio of rho 2 by rho 1 in terms of theta was given. So they gave theta and they asked the other value. So you can also do the same thing, like 1 minus tan theta upon 1 plus tan theta become something like that. I hope so.
So it will be sin theta plus cos theta upon cos theta minus sin theta.
Something like that. You can just check. I mean, yeah, sorry. This is opposite. So this is the tube problem, and this concept, this dive in and dive out method can be employed for the accelerating tubes as well. Once you know how to write the pressure in accelerating and rotating tubes, so you can do that as well. So let's do some more interesting question from the same equilibrium, which is very interesting. So let me draw uh, an equilateral triangle. And we have three separate liquids. So the size of the triangle is L length. Let's call it L. And the liquid length is all same. So all are of L length. So we have three liquids of length L, L, L each. So the way they are arranged is something like X, and then L minus X, then again X. I hope this length part is clear.
Yes, sir. So we can calculate further.
Pardon? So question is, if the densities are in AP, then find the X. if densities of liquids are in arithmetic progression, then so you have to find the x, and you can also understand which one is the densest and which one is the lightest. Correct.
Yes, sir.
So the green one is the green one is
Least denser.
least dense, and the pink one is
Most denser.
correct. So now you know in what sequence we have to write the answer. Like assume the density, you can do that. So go ahead and solve this.
only L is given.
Yes, only L is given. So answer must be in terms of L only. Okay, so I think you have taken enough time.
Sir, can you just give 1 minute, please?
Okay, last one.
Sir, I'm getting the answer as x is equal to 2 rho 2 L divided by rho 2 plus rho 3.
Oh my God. So this was the arithmetic portion, AP, not GP. Are you taking GP?
No, sir, I took AP only.
Okay, fine. So the way to write is simple. Write the pressure here, write the pressure here. Because the horizontal part will have no difference of pressure because it's the same level. So how to write it? So you can write as, let's say the densest is rho 1, the lightest is rho 3. Rho. Okay. So we can write a rho 3 and x. Okay, the sine 60 will cancel out from both sides, so I'm not writing. And you can also understand rho 2 into, and that's it. On the on the right side it is this.
Sir, but why did we assume that rho 1 will be the heaviest?
It is at the bottom. So the denser liquid will be at bottom, isn't it? Imagine the rho 1 is on the top side. It will always push it back, and eventually the only equilibrium case will be when the densest liquid is at the bottom, isn't it?
So it will push through the other liquids and go to the bottom.
Yeah, exactly. No matter what, you see, the equilibrium will be only achieved when the densest liquid is at the bottom and lightest is at the top. And you can, from the diagram, you can see the lightest is the green one. Okay.
Yeah, sir. So that's why my answer was wrong, I think.
Yes. So now we can write as the rho 2 is the average of the two because it's arithmetic mean. So we can write like this. And what you're supposed to do is just substitute the rho 2 value in the first equation. So let's call it equation 1 and 2. Just a minute. Just a minute. Okay, so now let's substitute. And once you substitute, I think you will be able to answer this question easily. So take the rho 3, this x term. So rho 3 minus rho 1 into x. I'm taking the x term one side. And so the rho 3 minus rho 1 plus rho 3 by 2 into L minus x. This is fine. Yeah. So this will be 2 rho 3 minus 1 minus rho 3, which is rho 3 minus rho 1 itself upon 2 into. And you can see this will cancel this out. That's interesting. So we have 2x equals to L minus x. So x equals to L by. So this is tricky question to solve. Although the answer is pretty much simple. It's L by 3. In fact, the diagram is very much the drawn in at such a right scale. It's L by 3 roughly. Yeah. Okay. So now we can go to the next concept called Pascal's law, which is pretty much simple, but very useful. So Pascal's law is simple. What it says that that whatever you create, like whatever pressure you create at one point of a liquid, that pressure will transmit throughout the volume. It's like the liquid will act as a channel through which you can broadcast the pressure. So this is something like a broadcasting of pressure which you develop at one point. So in a way, you can say that the liquid is not going to, keep the pressure at one point or concentrated at one point. Rather, you may develop anywhere, but the pressure will transmit throughout. And it is having a lot of interesting points. So the heart is working in a similar fashion. So it creates pressure, and you can imagine the number of veins in the human body. So how we can regulate the blood flow through different arteries or veins? And thanks to the Pascal's law, I mean, of course, Pascal's law is the inference which he drew, but it is the heart which creates the pressure at one location. Heart is at one location, we all know. But although the pressure is developed at one point, every single arteries or vein of human body is able to receive that extra pressure, and that is how the flow is established throughout the infinite arteries or the veins in the human body. So that is the beauty of Pascal's law, that you create a pressure at one point, and no matter how remotely the point is connected by the liquid medium, the role of the blood is to carry the pressure everywhere, and that is how the flow is established. So definitely, if we have the blockage in the artery, and if the pressure required to move the blood through the artery is getting difficult because of the viscous issue of the flow also. So viscosity reduces the flow. So that is why we need to have the arteries of finite dimension for the liquid to flow, or in fact the blood to flow actually. So when the flow will be disturbed, then various things happens, which we know, that heart attack and the brain hemorrhage, various things. So the proper flow of blood is essential. Proper flow of oxygen is essential for the working of human body. So although this is simple law, but the consequence is tremendous. Okay. Similarly, I mean, in case of hydraulic lifters like JCB, which is very famous, that's why I use the JCB term. So in case of hydraulic lifters, the lifters only create the pressure at one particular point. So they have something like a pressure box. I mean, they press it, and because every other channel is connected with the same box, so pressure is received by everywhere else. And once you release that part, it will start moving. So pressure is anywhere there, and you just switch the you unlock the part and it will start moving, and that is how the entire JCB is designed. You create a pressure at one point and it transmit the pressure through the tubes through which they are connected, and the force is transferred to the point. So that is the basic Pascal force. You can imagine that from human body or our functioning till the functioning of machines, the liquid is a fantastic medium to broadcast the pressure. So it is like you create at one point, and then the liquid will make this sure that whatever you have created is not limited to that point, that is available to every other point of the liquid. So that is how, let's put in words. So we say that any. Now, also you need to remember that the liquid will have its own default pressure. So the liquid is under some pressure all the time. Now, what you're creating is over and above that pressure. Understood? So if you are at a depth of h from the free surface, we have already a pressure of rho gh. Now, what you create will be the added to the rho gh. So it will be rho gh plus what you create. So any excess pressure developed by the liquid, developed in the liquid. Now. So any excess pressure developed in the liquid gets transmitted throughout the volume of liquid without getting diminished. So it will never diminish; it will remain same. Understood?
Yes, sir.
So we have mostly hydraulic lifters. So let me create the one. So now you can see this is the two you can say uh, places which we can where we can apply the pressure. So generally we apply the pressure near the small cross section using some pressing device. So you can use some anything to press. So once you make the pressure here, once you apply the pressure here, the pressure which you develop, the extra pressure which you develop on the left side, this pressure will get transmitted throughout the volume, and the same pressure, let's say this is delta P, the same pressure will appear here as a bonus. So it is appearing everywhere, but I'm not representing. What I'm representing is the end point where I'm interested. So this is exactly how the garages uses the hydraulic lift for the cars to raise. So okay, let me put a car here. It's a really big platform. No. So now this delta P will reach here over and above the pressure which the liquid will have automatically. And this pressure into big areas because the the area on which you're putting is quite a large area. This is the small area. So if the weight of this car, if the weight of this car is equals to the delta P into A, then we can lift it. So we can say that delta P into the area is equals to the weight of the car. So let's call it big W. Okay. In. Now to create this delta P, I imagine that we have a small object here. We put a small weight of W. So we can say this delta P is equals to how much? The weight which you have put upon area. And from these two equations, what you can write? That W upon area into capital A. So you can see that's very interesting answer that W by small a is small W by small a is big W by. So if you put a load on a wide area, it will have a less pressure because bigger the area, more the distribution of weight, and so the lesser the pressure. And if the pressure is small, then you can understand that it can be balanced by other pressure. So what really matters is the pressure to lift the car. So if the car is put over a big platform, so car cannot create a high pressure because the pressure is distributed. For example, can you stand on a iron nail on a pointed side?
No, sir.
The answer is you can stand if I put infinite iron nails. So if I take a board and if I put nails everywhere, so there won't be any difficulty in standing over it.
Yes, sir.
Because in that case the pressure is not at one point or other, it is your body weight is distributed over the large area, and because the body weight is distributed, so you're not creating, I mean, you're not experiencing enough pressure to penetrate the skin. So the iron nail cannot penetrate. So however pointed it may be, it will never penetrate until the pressure is distributed over the large number of nails. So every nail will act as a holder of your weight. So each nail will get the less weight. Okay, so that will not be enough to insert. So what matters is the distribution. And similarly, what we are doing here is by creating a pressure, a small pressure, transmitting through the liquid, and then we have a large piston over the entire car is kept. The piston is so large that the effective pressure that we develop is as good as the pressure that we develop on the left side. And because of the equality of pressure, we can lift it easily. So this idea is always there. Understood? So now this W by A is W by capital W by capital A. So what we are equating is the pressure that they are trying to develop on each side. And if they're equal, we can lift. So by slightly increasing it, I can lift the entire car. So car doesn't matter, what matter is the pressure. So we can make a bigger platform And now you may imagine that, sir, by making the area very small, we can actually lift anything. But the answer is no, because in the chapter of elasticity, you also studied about the strength of material, and therefore the body of the hydraulic lifter cannot sustain pressure beyond certain value, because the moment the pressure will go beyond the value, the entire system will collapse. So even the iron is not very strong as we perceive. Iron can be tear apart by the pressure. Okay, so anything can happen. Liquid is really powerful. You do not know the power of liquid. If you don't know the power of liquid, think about tsunami. So liquid is so powerful, it can crush anything, it can damage anything. It is very dangerous. In a pressure cooker, earlier there used to be very, large number of accidents. Okay. So then later on, the safety valve was introduced. And what is safety valve in pressure cooker? Something like, you can see a hexagonal
Yes, sir.
patch, and this part is very weakly welded with the lid actually. So if the pressure will exceed certain value, this will be thrown away, and it will create an open hole, and all the gas will leak out and pressure will drop. Without safety valve, pressure will build up, and because the actual valve, this is kind of locked, because this is a tiny hole, and if some food grains get stuck here, so the pressure will keep on increasing, and eventually if the pressure cannot leak out, so it will just blow up the entire. So the safety valve makes sure that beyond certain pressure, this will open up and things will be in control. It will not create the damage. So it is like the weakest link in the pressure cooker, and the weakest link is the safety valve. Okay, so I hope this is clear.
Yes, sir.
So pressure is very, very important concept, and we should know about it. So this is a simple Pascal law, and all the hydraulic lifters work on the this principle. Let me draw a very nice example.
The call from Mads Promotions.
So now we have a liquid filled in this entire volume, and we have a piston here. Okay. So imagine we have this kind of arrangement. So this is like you can say this is the heart, and we have the 4 different arteries which is linked to the heart. So if you apply pressure here or some force here, let's say all are having equal area. So by applying force here, we create the extra pressure of F by A. So without your knowledge, the pressure will reach here also. It will reach here. It will reach here, and it will reach here. So you are creating at one point, but it is not confined to that point. So it is going everywhere else, and because the pressure is reaching here, so to stop this piston from moving, we have to apply how much force? F, because it's the same area. So now, why I asked this question? Because you may think in a different way. Let's say we have 4 different valves, and they may ask you how much pressure is created if they apply force from all 4 directions. What is the delta P? They may ask this question. What is delta P? So you may answer that is it 4F upon like 4 times F by A? Because every force is creating that is. The answer is no. We can take only one. The reason is rest are balancing it. So delta P here is only F by A, although we can see there are 4 different piston and we are applying force F, F, F. But the other way of thinking is that if one will create the pressure F by A, to balance the other piston, we have to apply the same force F, F, F.
So I
Correct?
didn't understand.
Imagine you create a pressure here. So as per the Pascal's law, this pressure will transmit here,
Yes,
here,
sir.
here. So how much this piston will experience the force?
F by A.
A by A into A.
Yeah.
So how much force we need to apply externally to balance it, to keep the piston at equal
F.
F only, na?
Yes, sir.
Same here, same here. Is this clear?
Yes, sir. Understood.
So here the extra pressure is F by A only. It is not 4A by A. That is what we generally get confused with. That's why I asked this question.
Sir, and if we do not apply F force in all in 3 sides,
It will
then
accelerate. It will accelerate there.
yes, sir. So then delta P will be 0.
No, delta P will not be 0, no, because the pressure will act and it will accelerate. It will accelerate the piston. If piston is massless, then things will be different. Then it will have infinite acceleration. If it is having some mass, it will have finite acceleration. Okay.
Yes, sir.
Anyway, so now you can understand that how exactly it works. So we can create a device with, I mean, a point to exert pressure, and then we can create tiny holes here. So maybe we can create a sprinkler. And it's very simple to design. So what you do is you create a piston system to press it. So once you press it, the pressure will reach here. And because of the difference of pressure, the water will accelerate. So water will accelerate, it means it will gain some velocity. And when it will come out of the system, it will have very high velocity, so it can go far distance. So we use nozzle for the same purpose, for spraying purpose. So everything is designed with the same Pascal's law. So most of the sprayers or sprinklers, I mean, what we use is the Pascal's law and the Bernoulli equation. Of course, we have two steps. One is the creation of pressure, which is getting transmitted, and then the drop of pressure leads to the acceleration of the liquid. That is called the Bernoulli's equation, which we will study later on. So Bernoulli equation is basically the same thing. You You decrease the pressure directly, and that loss in pressure will become gaining, you can say, speed. That is called dynamic pressure. And the pressure which I'm saying is called static pressure. Later on, we have to differentiate the two terms. So the pressure which you have so far, kind of understood or have the intuition for, is actually called static pressure. In physics, we have different name of the pressure. We have static pressure, we have dynamic pressure, we have hydrostatic pressure. So we have various names, and from the context, we can understand which one is correct, which one is, and what it refers to. We can understand. So, okay, there are a lot of practical application, but theoretically, it's pretty much simple, and we can leave this part. So, if you want to design some machine, something like that, you can do so. Okay. So, yeah, this is used for gardening. If you have the low height tanks, let's say if you have a tank at home, and the pressure by the tank will not be enough. So, what we do is we attach a motor to the tank, and we close the tank. So what the motor will do is it will create the pressure by thrusting air into it. So let's say we have a motor which can suck air from the atmosphere and will press it to a desired pressure. So even the water will, if you from a tank, the water will come down. So the pressure is rho g small h, because it is small h. But the closed tank, we can have air and we can fill more air to create the extra pressure, and therefore the pressure here will be rho g s plus the pressure that we create through air pressure, and therefore the water will leave at high speed. So this is how we create the the pressure. Okay, so these things are required,
Yes,
and
sir.
we have devices available in the market. You can go and ask. These things are freely available, so you can design a lot of things. Okay, if you have space, time, and everything else, the resources. So, okay, Pascal's law is not a big deal. So, I think we are done with the Pascal's law. I will not go in detail more than this. Uh, you can go to something new concept. Okay. So, the next concept is pretty important, and that's called force and torque analysis. So, you can imagine that the human body is entirely, like a large portion of human body is liquid actually. So, we have different types of like RBC, WBC particles, which is flowing within a liquid system, which we call blood. So blood is not just liquid; it is liquid with a large number of particles, tiny microscopic particles. We have hemoglobin, which is a carrier of oxygen, and hemoglobin itself is the complex compound of iron. It's a cobalt and iron complex compound, FeCO something, CO6, I think. And it carries oxygen because it holds the oxygen as a, because it's a strong ligand, and the CO poisoning. Okay, those things are not required. So the blood itself is a flow, and flow demands laws of Pascal's law, Bernoulli equation, and Poiseuille equation. All these things are followed within the body itself. So in a bypass surgery, what happens when an artery is blocked completely? What they do is they create an alternative channel actually. So we call bypass. So you make a you can say synthetic artery, which called stensis nowadays. And if this route is blocked, if I know this is blocked, so the liquid can flow properly. So we create the alternative, and then blood can make a way like this. That's it. Okay, and then the heart can start functioning in a regular fashion. This is called bypass surgery. It used to be very expensive. I think nowadays it is slightly lesser. So basic laws of physics is working in medical science, but okay. The problem is we have less capable doctors to implement it on a real life, on a human body. So that's why they are. This is expensive job, but I think uh, it is very easy job, technical. So force and torque analysis. So we have to do the dam problem, like dam. So we do the dam. Okay. So generally, this three-dimensional picture will not be there when you solve numerical. But let me show you how the dam thing will look like. Okay. Okay. This is the cross-sectional view. You can see this is uh, the full view, and so in examination you will be only given the side view, not the full view. So imagine we have a okay. So I think we should go into here. Okay. So you can see the water, right? Everything you can see. This is quite visible. So this is the dam. This is the water, and definitely there is a part which is being touched by the water. So I can say that this is the part which is getting touched by the water. This is the part, right? So this part of the wall, you can see it's pressed by the water. Water is pressing it, right? And this liquid will have some depth. Let's say H. The dam will have some width. We can call it a W or L. So the better is I will say L only. Okay. And the rest is the structure which is not required. So this is the actual diagram, and this is just for your understanding that you can feel something. You can visualize how it looks like. Now let's come to the actual diagram that you will see in book and also in numerical. So definitely this diagram will not be given to you for sure, and you have to remain happy with this simplified diagram. So the rest is up to your imagination. So this is how the diagram will look like, and they'll mention the height h. So as you go down the dam, as you go down, what will happen? So pressure will increase or decrease? And it will increase proportional to height or by other relation? I think it's a proportional relation, right? So what I'm representing is the pressure due to the liquid itself, not other pressure. And we can draw a diagram like this. Pressure will grow in value as you go down. And the arrow is representing the magnitude of pressure. So as you go down, pressure will grow, and we can represent by the varying length. And it is increasing proportionally, so we can draw a straight line. So it means the length will grow proportional to the depth. So this y by this p will be same as the y dash. I can say p dash. So you can say p and y are proportional, p dash and y dash are proportional, and so on. And we know the pressure formula is due to liquid rho gh. So I'm interested in how much pressure the liquid is creating. Okay, we do not consider the pressure due to the atmosphere, because the atmosphere will press from this side, and the atmosphere will press from this side as well, and both will balance out eventually. So that's not an issue. Yeah, that's not an issue. You got it right. So the atmospheric pressure we will not consider. We'll only consider the liquid pressure. And the question is, what is the total force exerted by the liquid on the dam wall, the wall of the dam? So what is the F liquid? So you can take a strip at a certain depth. So you can go y and cut a dy. Okay. Because once you go y below, you can easily see the entire strip will have same pressure, and therefore you can add the force df. So df will be how much, tell me guys? What is df liquid? Force equals to pressure into area.
Yes.
So what is the pressure? For the entire area, the pressure is same rho gy. What is the area?
So the flat is
Area of the wall, the shaded portion. You can see the small strip. What is that area?
LD.
Okay, so now you can find the net force by integrating it. The F due to liquid will be rho gl y dy integration from where to where? From 0 to h. Correct. So if
Yes.
liquid turns out to be, that's it. Is this clear, guys?
Yes.
So this is the basic method, method one. Let's call it method one. So anyone having any doubt in this question? So the imagination part will be yours only. I mean, of course, no one is going to give you this explanation. So they will give you this diagram and you have to solve this question. And even the width will be mentioned as L or something, 1 unit and something. You can just use that. Okay. But this question can be solved in a variety of ways. This is the fastest method. So we have a dam. Just do the basic diagram, not anything complicated. So this symbol means the water level. So this is the engineering practice which we need to know. And yeah, the height is given as h. So that is one thing given on this. So we have seen that if we take y and but a dy, y dy. So what you can write is the pressure is how much? So we know the pressure is rho gy. So force, how much force we wrote? Df equals to
Rho GH
dy.
Rho G LDY.
So we can write F equals to rho gl y dy integration from 0 to h. Okay. So this we can also write as rho g y l dy. Correct. And this we can also write as y dA, because l dy is called dA. Correct. Now this can be rewritten as, if I divide by by dA, and if I multiply with dA, this is same equation. Okay. So we have a nice expression for force. F equals to rho g y dA upon dA, whatever. So this term, you know what it is called? Let's say remove the limits, it doesn't matter. So in center mass chapter, we have studied something called the area moment. So if you remember the YCM formula, it was YDM, the mass moment upon dm, and this you can convert into area moment by writing YDA. So basically the force on a wall due to liquid is rho g into YCM into whole area. That's easy answer. So next time you need not to calculate the everything, just find the pressure at the center mass location of the area on which you want to find the pressure, find the force, and multiply with that area, and that's the answer. Is this clear? So
Yes.
you have to just use this formula directly. So find the pressure at the center mass of the given area on which you want to find the force and multiply with the whole area. And if you apply the same, what you can write? So the wall was rectangular, center mass will be here. So this must be h by 2, correct?
Yes.
So convert h by 2. That's it. Pressure at the center mass. And area was what? L into h. You see, it's the same answer. So you can see the answer here. You can see the answer here. It's same. So this will have a lot of advantages in solving problem. So imagine we have a scenario like this. So doing the calculation is a really challenging task. So we can do this trick and we can get the answer. So we have a wall. You can see this wall is basically filled with liquid. It is completely covered with the liquid. Just to represent this wall. And this is two-dimensional view. And what we have is we have a secret door at the bottom of the this wall. Okay. So now if I say the radius is r of this gate and the depth of this from the free surface, if I say this is h, and we are asking what is the force acting on the gate by liquid. So how much force is acting on the gate by the liquid? You can understand this question. So if you try to solve by the integration, it's really challenging for you. It's not impossible, but it's just too challenging. But the other method is pretty simple. So can you see the center mass? I think yes, you can see the center mass. Center mass is how much? What is the depth of center mass from the free surface?
H by 2.
So this is h minus r. I'm asking the gate, not the entire wall. So now my only interest is gate. So what is the center mass of the gate? So this is YC. So the pressure there will be how much? Rho g h minus r into area of the gate, which is pi square. And this is the answer. Understood?
Yes.
So I can make any shape. Okay, so maybe we can create something like this. Interestingly, a triangular gate. Let's call it, this is 1, this is 2, and this is L, this is L, this is L, equal side. So maybe this is a one question. What I can do for two question? So for the second case, what is the force? How much we can write? Tell me the answer. The gate is at the bottom.
So we say rho G H minus L sin theta into so the answer.
Yeah. So the answer will be
Rho G bracket H minus root 3 L by 2 bracket plus root 3 L square motion.
this is L sine 60 into 1/3, right?
Yes.
So L by 2 root 3, correct? So center mass is at centroid, and the centroid is 1/3 of the vertical height, correct?
Yes.
And the vertical height is L sine 60. Hmm? So this is the pressure at the centroid, and into area is root 3 by 4 L square.
L square.
So you can see that method 2 is really powerful, which helps in solving any problem, and that's interesting. So if we talk about the dam problem that we have just solved, so this is, so this is a slightly advanced concept from the BTech first semester. That's called the load diagram method. But I found this very useful in solving the the torque problem. So we'll see that how it is so useful. So in a load diagram method, the pressure is called the load basically in the term of engineering. So if you draw the pressure diagram, so if I choose the pressure as the x-axis, So if I call this is like, let's look at this is pressure axis, and this is the depth. So this is y, this is p, and this is origin. So we have seen that pressure will increase as you go down. So this is the pressure. So when you plot the pressure diagram, it's called the load diagram. And this diagram is like a triangle in which we know the the height of this triangle. This is h, and this is how much? How much is this? The bottommost. So bottommost will be how much? What is the bottommost part? Tell me, guys.
So the angle.
The bottommost length is how much? It's pressure, only pressure diagram. No? So as you go below, the pressure will increase. When you are h below, how much is the pressure? It's a pressure axis. Come on.
No,
It's a rho gh. So this is the rho gh, and this height is h. Is this clear?
yes.
So what is the area of load diagram? The area of load diagram is how much? Half into base into height. Which is rho gh square by 2. So the area of the load diagram gives the force per unit width. So force due to liquid is defined as area of load diagram. You can say width. So force due to liquid is actually area of load diagram into width. Because what you're looking is the cross-sectional view, and the dam is spread within this, which you can see. And therefore the answer will be rho gh square by 2 into L. And again, this is the same answer as we derived earlier. Let's call method 3. Is this clear?
Yes.
Okay. So now we can do the torque analysis, which is pretty easy. So first we'll do from the scratch, and then you can do the way you want. So if we have a dam, okay. So if you want to find the torque, the height is given, the width is given L. About the bottom, I want to talk about the axis passing through the bottom along the, of course, this line basically. if you draw a line. So what is the talk about this line? So we can think in two dimensions as a point, and that's not a bad thing. So find the torque about O from the scratch. This is not difficult, you can do it. So the way you did the force from the scratch, you can do the torque from scratch. Find the force at a elementary strip and then find the torque about the O due to that force and then integrate. Done, guys?
Yes.
Anybody doing this question? Anyone doing this question or shall I solve this? Tell me.
So I'm stuck in one equation.
So you can go back to the first derivation of force here, this one. So if the force is acting here, dF, what is the torque of this force about the bottom? Think this way. So you know how to write df. Then what will the torque? So this df will get how much torque about the bottom? You can say
It's
this
first one.
df cross df into
dr. Then we can integrate from
df into
h.
df into
ds into dh.
df into you are not getting any sense actually. So what is the torque about the bottommost point? If you look at the 2D figure, then you can get the answer. So maybe this is the df. So what is the torque about O? What is the torque about O? I think rotational dynamics we have finished already. Yeah. Anyway, so you guys are clueless now. So let me show. So this height is h minus y. So the simple answer is the torque will be. So if you choose a point y below, and if the force is df, the torque about the bottom will be force into the distance from the bottom, right? That's simple. So d tau about O equals to df into h minus y. And df is rho gy, which is the pressure into area, which is L dy into h minus y. Sorry. So rho gl y h minus y into dy, and then we integrate from 0 to h to get the net torque. So the net torque will be rho gl, and this is hy integration, which is hy square by 2 minus y cube by 3. This should be h cube by 6, I think. Yeah. So this turns out to how much? Rho g h cube l by 6. Yeah, this is the torque. So the liquid is creating this much torque about the bottom. If you have any difficulty in understanding this, let me know. It is clear, guys.
Yes.
So I think you guys need to, do this thorough revision and practice this question, because uh, I expected that you guys can do the basic integration, but anyway. So there is a method 2 again from the BTech first semester.
Yeah, I took height as dh and then I tried to integrate from 0 to h. So that's my thing.
Okay. So first you need to write the torque due to elementary force acting at some random location, and then okay, you need to just integrate. So method 2 is very easy. So what it says that just like center of mass that we studied in center mass chapter in mechanics, we do have a concept of center of force. So just like center mass, we have center of force, and center of force is determined by the center of load diagram. Okay, so center of force is determined by center of load diagram. And if you remember the load diagram, it was something like this. Okay, so this was the load diagram. I hope you remember this. And because it's a triangle, so we can say that if load is increasing proportionally, then the center of load will be exactly h by 3, just like the center mass of the triangle. So we have center of load actually, and we can say that the load is concentrated at h by 3. So this is how we assume. Let's call it center of load because the load diagram is a triangle. This must be, we call it h by 3. So the net force we can think to be concentrated here. So the force due to the liquid that we have already calculated, we'll assume that it is acting here. Okay. And therefore the torque about O we can just write as F liquid into h by 3, and that we're done. F liquid, if you remember, was the pressure at the center, rho g h by 2 into whole area, which is h into L, and then h by 3. And if you just multiply, you can see the answer is exactly the same. So this is a really advanced method. It prevents the doing the integration and all. You just need to remember it is h by 3. I mean, in fact, your entire syllabus is very much like this. You can just remember, in fact, h by 3, and you can do the question. Okay. Is this clear, guys?
Yes.
Yeah, slightly difficult, but okay. So you can do it by scratch method, or you can do this way. It's up to you. Okay. So before I end today's lecture, let me do this last one. So we have a gate and we have a water on the other side of gate. And the gate is, you can imagine this is like a, I mean, how to imagine? Always have to think of three-dimensional world. The water is filled here. Okay. And this gate is hinged about the center. So this is the hinge point. So it means it can rotate like this. Okay. So this is, I mean, the idea. And this length is L, this length is L. So I can say the depth is L and this is also L. This is what I have assumed. The density of the liquid is rho. And the left side is liquid. So what you're looking at the side view. So you're looking from this side. I hope so you can understand this. Okay. Oh, I need to remove this. Oh, all right. The density of liquid is less than rho. This is the width of gate, and the height is, and it is hinged at the center. So hinge means it can rotate about this center, either clockwise or anti-clockwise. So what do we expect? Like, yeah, what do we expect? The gate will open this way or this way. If I release,
Anti-clockwise.
so one or two, which way it will open? If I release the gate,
One.
one, correct. Because as you go bottom, the pressure will be more. So below this hinge, we have greater pressure, and above we have less pressure. So the force at the bottom will be bigger than force at the top, and therefore the net torque is bound to be, okay.
Yes.
So the question is, what is the minimum force that we need to apply at the bottom? Not minimum, just F. So what? How much force we will apply here? It's unknown. To keep the gate vertical. So think for a while, then also. I hope this is clear to you guys. Question is clear.
Yes.
So anyone want to attempt this, or shall I solve it right away? Tell me.
No, no, no. So can you show the previous question? Done. Rho G L cube by 3.
How much?
Rho G L cube by 3.
Rho G L cube by.
3.
I think this should be the correct answer. So what you did?
The torque is equal to F cross R and R is L by 2.
Correct. So the net torque we have to balance. So F into L by 2, and this will be balanced by
The rho G H at the bottom.
Rho G L cube
L to bar 4
L power 4, yeah, by 6. Correct.
by 6. Yes.
So the answer is very much correct. Rho G L cube by 3. Because the center of liquid force will be somewhere here, and I think where this is where you went wrong. And you can look at this. This will be how much? How much is this? This is L by 3. So this is how
3.
much?
L by 6.
L by 6. Correct. So now you understand that you're finding the torque about O, not the bottom, and therefore the answer will not be. So this part is wrong. Okay. So what you're supposed to write is F into L by 2, because you're finding the torque about O, which is 0. O is center, and the liquid will be F liquid into L by 6. Understood?
Yes.
And so the answer is the F is always F liquid by 3. Okay. So F liquid is how much? Rho G L by 2 into L square. So I hope this is clear. So F is how much? Rho
Q
G
by
L cube by.
6.
So this is a common mistake. Don't worry. I mean, I was expecting expecting the same one. So now the question is, what is the hinge force? So can you find the hinge force? So this is done. So now we have a next question. Can we calculate the hinge force? And the answer is definitely yes, we can calculate because if I take a gate as an object and then we can draw the force, so the hinge will, because the water is pressing the gate towards right, so hinge will apply force left. And then we have a liquid force acting towards right. And we have just learned that this force is how much? F liquid by 3, right? So if you write the equilibrium, we can say F hinge plus F liquid by 3 is actually F liquid. So F hinge is how much? It is 2 by 3 F liquid. And so this is 2 by 3 into rho G L by 2 into L square. This is rho G L Q by 3. Yeah, this is the answer. So there are a variety of questions we can do. So we can bring the what do you say, rotational dynamics a lot into this topic. So if it is a torque, then we definitely have the rotational dynamics, and we have to be just think about the center of force by looking at the load diagram, which you can virtually create for yourself in your brain, or you can put on a paper. So there are only two types of load diagram that you have to face. One is a triangle, or other is a rectangle. And rectangle is very simple. Center mass is at the center. So okay, I have one more question to deal with. Shall I give it now or later on? I think I should give it. All right. So you guys can practice, revise, and you can start solving basic problem. Of course, the Archimedes principle is left. Then you can do a lot of questions. So what we are doing is mostly JE kind of problem. So JE will be asking question of equilibrium and force analysis and all. And unfortunately, those kind of questions are not present in the SC Verma book. That's a big problem. So I will try to find the question which I have, in fact, and I will try to send you. You can practice those questions at home. Bye, guys.